Endovenous laser thermal ablation, or EVLA, is a common treatment for varicose veins. But have you ever wondered how it really works? I used to think, like many others, that it was all about the laser targeting either hemoglobin in the blood with shorter wavelengths or water in the vein wall with longer ones. Classic selective photothermolysis. Turns out, that's not quite the full story. Let's break down what's actually happening inside the vein during EVLA. First, recent research and mathematical models show that the initial heating of blood and the vein wall is actually independent of the laser's wavelength. That's right, whether the laser is tuned for hemoglobin or water, the temperature response is the same. Now, you might assume that the inner wall of the vein absorbs most of the laser's energy, but in reality, direct absorption by the vein wall is pretty limited, and almost no photons from a 1470 nanometers laser even reach the inner wall. In fact, even in a totally collapsed vein, direct photothermal effects account for only about 20% of the energy increase at the wall. So what's actually responsible for the main action? It's the blood that's left inside the vein, the intraluminal blood surrounding the fiber tip. This blood absorbs the laser energy and heats up to coagulation temperatures, no matter which chromophore, hemoglobin, or water is the primary target. Here's where it gets interesting. The dominant factor in vein closure isn't how much light the wall absorbs, but how heat transfers from the hot layer of blood coating the fiber tip through to the vein wall. When the laser is fired, both hemoglobin and water in this blood absorb energy, about 15% from hemoglobin and over 60% from water, generating enough heat to cause irreversible thermal damage to the vein wall. Now, let's talk about the benefits of using longer wavelengths like 1940 nanometers. While they don't dramatically increase direct wall absorption, they do have some clear advantages: less pain after the procedure, less bruising, and a lower risk of thrombus formation. Why is that? It all comes down to the optical extinction coefficient of blood. At longer wavelengths, blood absorbs more and scatters less, making heat transfer far more efficient. This efficiency means I can use lower power settings to get the same effect, reducing the risk of complications like vein ulceration or perforation. So the next time you hear about EVLA, remember, it's not about the laser wavelength hitting the vein wall directly. It's all about the blood around the fiber absorbing the energy, heating up, and transferring that heat to the wall. That's the real mechanism behind successful vein ablation.